we should talk about applications of scalar line integrals. As it turns out, there aren't too many applications of scalar line integrals. In the next section, we'll be doing vector line integrals, and that will have a lot more applications, a lot more physical interpretations. I do want to hit in this video one important application of scalar line integral, and that is integrating density to find mass here. So take a look at this problem. Find the total mass of a wire in the shape of the parabola. Y is equal to x squared. X runs from 1 to 4. And the mass density is given by delta of xy is y over x grams per centimeter. I guess we're measuring x here and x and y in centimeters here. And so the formula that we end up caring about here is that the mass of our wire is equal to the integral from like a to b. Well, let me just kind of say integral over c of delta of xy ds, and we would go through the exact same process in this problem as we do in any of the other scalar line integral problems. So we have to get a parameterization down, take our parameterization, substitute into delta. So now delta just is depending on t, not on x and y, multiplied by the magnitude of the derivative of the parameterization. And when we do the integral, we end up getting the overall mass. So integrating density gives you the total mass, and that should make sense. Okay, so let's go to the next slide here just to draw a picture here. So this is a chunk of y is equal to x squared, where x is running from 1 to 4 here. We need a parameterization. We need a parameterization of this curve here. And so I think we can do r of t is equal to, so x runs from x, we can just replace x with t. And so t will be running from 1 to 4. And if x is replaced with t, y will equal t squared. So here's our parameterization. R prime of t will equal 1 comma 2t. And so the magnitude of r prime of t will equal the square root of 1 squared is 1 plus 2t quantity squared is 4t squared. Okay, so we got r prime of t. Now let's do delta plug in x and y are the components of r of t. So delta of r of t here is equal to y over x. Well, y here is t squared, x is t squared divided by t is t. So our mass is going to be the integral from t runs from 1 to 4. Those are our bounds on t. Delta of r of t is t times the magnitude of r prime of t is the square root of 1 plus 4t squared dt. Okay, we should be able to do this with substitution here. We let u is equal to 1 plus 4t squared. Du will equal 8t dt, or du divided by 8 is equal to t dt. So there's du divided by 8. Okay, so mass is equal to the integral of u to the 1/2 power times du over 8. When t is 1, u is 4 plus 1 is, 1 plus 4 times 1 is 5. When t is 4, 1 plus 4 times 4 squared is 65. And so we end up with, let's see here, 1/2 goes to u to the 3/2. Divide by 8, also divide by 3/2, and you end up with 1/12 u to the 3/2. Plug in u from 5 to 65. So this is just going to be 1/12 65 to the 3/2 power minus 5 to the 3/2 power, and we can just leave it like that. If you want an approximation, because it's a real life problem, it's about 42.74 grams. Okay, so integrating density to find mass. This is one of the most common applications of a scalar line integral.